Alrighty, there we are. Good morning, and welcome back to MAC2311 calculus. We've been having fun lately, learning a little bit about the derivative and starting to calculate derivatives. Thinking about the graph of the derivative is a very big deal. Today is an exciting day for us because we are moving into our first kind of set of, we want to finish up 2.8 a little bit, and then we'll be ready to start talking about our first collection of differentiation rules. So one thing I wanted to do today, we have not had the chance to do yet, is just look at a few more calculation examples. I only did one of those. Talk very carefully about differentiability. This is where we left off last time. And show you a function that is continuous but not differentiable. We'll look at some other ways the differentiability condition can fail. We can talk about higher order derivatives. And then next time, on Wednesday of this week, we will be having our next student teaching session. And I have had the opportunity to talk with, I think it's Radha and Natasha once, but we still need to meet again to go over you guys' lecture materials. So let me just make sure I have everything squared away here. Yeah, so on Wednesday, was our next class after this one, Natasha and Radha will be going over section 3.1, which is on the power rule and derivatives of exponential functions. Very exciting lecture. It's good stuff. It's like the one thing everybody remembers from Calc 1. But I would like to meet with you guys today, if possible, just to go over the actual lecture material itself. I have not yet this morning had time to clear out my emails. Did you guys by any chance send me your materials, the slideshows or videos, anything like that yet? Radha and Natasha?
Yes.
Have you guys had the chance to put together the lecture materials?
I have most of mine, but I thought we were doing it on Wednesday.
Yes, you are. You are doing it on Wednesday. Yeah, today is not your day. I was just trying to ask or confirm if you guys would be available to meet today, so we can go over that stuff and make sure everything is polished. And
what time?
My office hour is 1 to 2. If you're free, then that would be awesome. If not, you could always email me the stuff too. I just need a chance.
Okay. That should be fine.
Okay, very, very good. Alrighty then. Let's get in here and wrap up 2.8 then. Today may be a slightly short day. That's okay if it goes like that. Let me turn on my screen share. Here we go. All right, this is MAC2311, section OH1, which is Calc 1 Honors. Yay. The date today is the 13th of September, 2021. And today, we're going to finish section 2.8 on the derivative as a function. So you'll recall from last time that if I give you the graph of f, you can estimate the slope of the tangent line at a few points and use that to sketch a rough graph of the derivative f prime. We also talked about different notations, right? Like the prime notation and the Leibniz notation, the DDX. Oh, just remembered. There was, I think last time at the end, something I wanted to show you guys, that painting. I did eventually find it. Here it is, right? It was Legendre. It wasn't Laplace or Lebec or Lagrange. It was Legendre. This is the guy, right? Isn't that a fucking funny painting? This is the only picture of him surviving. And it's not like he was from a million years ago, you know, 1752 to 1833. There were photographs. There are lots of other portraits of people from that era, but this guy must have just been exceptionally shy and grumpy. And you can kind of really see that grumpiness here, right? Like, look at that frown. The full painting is this one, and it depicts Legendre next to Joseph Fourier, who was another famous mathematician of the era, originator of a thing called Fourier. We pronounce it the American way now, Fourier series. Really big deal in mathematics. Yeah, it's got to be an interesting legacy, right? Have everybody just remember you as like, but I don't imagine he minds because he refused to sit for any other portraits, and he chose to do that. So you know, that's that. Let's see, is there anything else that I'm forgetting from the end of last time? Let me just begin here by saying recall. We say f is differentiable at x equals a if the limit defining the derivative exists, right? And we know what that limit that defines the derivative is. I'm not going to go back through that. So a function f can be differentiable at some number, and it can fail to be differentiable at some number. And we saw a few cases of that, right? Like where we calculated the derivative. For example, we saw last time that if f of x is, what do we do? We did the square root, the cube root of x, whose domain is all real numbers, has derivative f primed of x, which was 1/3 times the cube root of x squared, whose domain is everything but 0, negative infinity to 0, union with 0 to infinity. So even though this function f of x is continuous everywhere, its domain is all real numbers, and it's continuous, that graph is connected, the derivative, and I'll show you how to do these computations, or actually Radha and Natasha will show you how to do this computation without any nasty limit stuff on Wednesday. His derivative comes out to this guy, which is undefined when x is equal to 0. And we did this for the square root function also. So that's the idea, right? This function may be defined and happy and healthy at all real numbers, but his derivative is not happy and healthy at all real numbers. He gets very upset at x equals 0. So this function, we would say, is not differentiable at x equals 0. And I'll say it like this: we may suspect that f of x equals the cube root of x is not differentiable at x equals 0, right? Because this derivative isn't defined at x equals 0. Yeah, Sarah makes an interesting point about the painting there. It is surprisingly candid for the time, right? In like Victorian England, everybody's sitting like this, you know, very stoic and stuff in their paintings. It's around the Napoleonic era, right? And all the paintings of Napoleon are very regal, but nope.
Every painting commissioned was like considered a work of art because how long it took and how freaking expensive all the stuff was. So that's hilarious that somebody put paint to that.
Yeah, it really is. I think he must have been an interesting fellow. I cannot imagine, you know, what that would have been like to be sitting around with him and Fourier and these guys and just see a grumpy motherfucker wishing them. But
Stands to reason.
Yep. Okay, so from examples like this, we suspect that this function might not be differentiable at x equals 0. There are even more clear examples, one of which I will grind through for you in all its gory detail here and now. But the big idea is that, yeah, the derivative might not always exist. there are some places where even though the function is well behaved, its derivative is not well behaved or just straight up doesn't exist. The obvious examples like these where the domains are different just by like analyzing the algebra are present, they exist. But there are also cases where things are a little bit more subtle. So let's look at one of those slightly more subtle cases. You may also remember we had a graphical interpretation of this that we looked at last time where the tangent lines are becoming vertical.
They dropped a power.
Yeah, that as well, right? When we looked at when we started sketching the graphs of the derivatives of nice integer power functions, we saw that those powers come down by 1. And there is something to that. But let's look carefully. I'm just going to state this. Show that f of x equals absolute value x is not differentiable at x equals 0. So again, here I have a function that is nice and continuous. Something else we talked about, right? Continuous means connected, differentiable means smooth. Nice and continuous at x equals 0. But we know the graph, it's not smooth at x equals 0. So we suspect that it's not differentiable at x equals 0. And we're going to show that. So I can remind you, the graph of the absolute value function looks like this. And it's not smooth here. So that's what leads us to suspect that this function is not differentiable at 0. But if you want to really show it or prove that this function is not differentiable at x equals 0, we got some work to do. Right? So what do I need to do? I need to show that the limit defining f prime of 0 does not exist. That's the task that's set before us here. So remember, f prime of 0 would by definition be the limit as h goes to 0, f of 0 plus h minus f of 0 all over h. And then for this function, that is lim h to 0. Please be in the good habit of always writing your limit. Don't skip writing this. Absolute value of 0 plus h, that's f of 0 plus h, minus the absolute value of 0, that's f of 0 all over h. And then those zeros are kind of redundant, right? 0 plus h, that's just h. So the top is just the absolute value of h minus absolute value of 0 is 0. And the downstairs here is h. In order for this limit to fail to exist, which we think is the case, one of a few things has to happen. One of the left or right limits would have to be infinity, or the left or right limits would both be finite, but not equal to each other. So in any case, if we're trying to check and see if this limit does or does not exist, we need to look at the left and right limits individually. So the limit as h goes to 0 from the right of the absolute value of h over h, what is that going to be? Well, if I put in numbers that are just a little bit bigger than 0, then those numbers are positive. So the absolute value of those numbers is just those numbers themselves. In other words, yeah, if h is just to the right of 0, then the absolute value of h is h You can cancel those. And like Yiping just said, what we're going to get out here is 1, right? Because h over h, that's just 1. And the limit of the constant function 1 is 1. So the limit as h goes to 0 from the right of this expression is positive 1. Now that's not the limit of this function, right? That's the limit of this difference quotient. On the other hand, the limit as h goes to 0 from the left of absolute value h over h. Here we're imagining that we plug in numbers that are just very, very small, but negative numbers that are just to the left of 0. So the
minus h over h.
right, exactly. Yeah, the absolute value of a negative number is the negative of that negative number. That's how the absolute value function works. It negates the negative values to make them positive. So this is lim, oh, I left off the plus there, lim h to 0 minus negative h over h. I left off the 0 plus here too, didn't I? Sorry. And just like you can cancel the h's there, you can cancel the h's here, but this time you're going to get negative 1.
So no limit.
Right. The left and right limits are different. So that limit does not exist. And what is that limit? It's the definition of the derivative of f at 0. So since the left and right limits don't match, the overall limit does not exist. That is, that overall limit is the definition of f primed of 0. So f primed of 0 does not exist, and that's precisely what we were told to show. And if you want to, you can think about this geometrically. If I'm thinking of h as being over here, just to the left of 0, then the slope that we're looking at there is this guy. It would actually sit right on top of that black line. As h comes in, this is always negative 1. And on the other hand, if you're thinking of h as being over here, then the slope that we're looking at is this guy, which would always be positive 1. So as h comes in from the right, the slope stays positive 1. As h comes in from the left, the slope stays positive 1. Sorry, stays negative 1. And those don't match. And it's precisely that lack of matching that gives us the not smooth behavior. So you see the failure of this limit to exist is identical to saying the graph is not smooth at this point. In other words, being smooth, differentiable, is the same as having the limit defining the derivative exist. What about away from 0? All right, this function is not differentiable at x equals 0. But what about at x equals 1, 2, 3, 4, 5, 10, pi? There, all is well. So I will go on to say a little bit more about this. However, f of x equals absolute x is differentiable for any other x values and has derivative f primed of x defined piecewise. -1 if x is less than 0 and +1 if x is greater than 0. There's a bunch of ways to get that. You can remember that the absolute value of x is just -x if x is less than 0 and +x if x is greater than 0. And then you could calculate the derivative of each of those pieces, or you can think about tangent slopes over here. That's sort of the more natural thing for what we're doing right now. If you take any x value to the left of 0 and estimate the slope of the tangent line along there, it's always going to be -1, right? This is a straight line. So the tangent line to that straight line is another straight line with the same slope. And the same is true over here. So what does the derivative of that function look like? The derivative looks like this. If x is positive, then it outputs +1. If x is negative, then it outputs -1. That's the derivative of f primed. Oh, sorry, that's the derivative of the absolute value function. Right here. And you see it's undefined at 0, right? F primed of 0 does not exist. On the graph or through the limit definition. This is 1 up here, this is negative. Other ways derivatives can fail to exist, like I said, if the slope of the tangent line is going to infinity. That's like what we saw with the cusps, right? Or with the cube root function. Anywhere that the slope of the tangent line is undefinable for whatever reason. Either there's a non-smooth portion of the graph where you can't say what the tangent line should look like there, or there's a portion of the graph where it's getting so steep that that tangent line is vertical, has infinite slope. Anywhere you cannot say for sure what the slope of that tangent line is as a finite value, we would say the original function is not differentiable. Any questions on this guy?
Yeah, sorry, could you repeat what you just said? I was making a note, but I feel like that was important.
Sure. So intuitively, a function is going to fail to be differentiable at any x value where you cannot say what the slope of the tangent line is, right? Because that's what the derivative does. It tells you the slope of the tangent line. So if you're looking at the graph of a function and you're trying to ask, where is this function differentiable? You're looking for locations on that graph where the slope of the tangent line cannot be reasonably defined. And that could be a pointy thing like this, or it could be a place where the graph gets very steep, where the slopes of the tangent lines are going to infinity. Those can look like pointy cusps, or they can look like the origin on the cube root function. Let me draw some. All right. So. We can kind of take it easy today. So spotting non-smooth behavior. Let me draw for you a few non-smooth things. Of course, that absolute value function, he wasn't smooth, right? This is no good. Another thing that can happen is maybe my tangent line becomes vertical for a second, like this. So remember the example of the semicircle where we tried to sketch the graph of the derivative? Or you can have what's called a cusp, like this. So cusps can come in several different forms. This function is not differentiable here, here, or here. Now that second one, I would have a little bit more to say on, but let's just take a second and say f primed of x would not exist at these points. All right. Here, here, or here. These guys are called cusps. Mostly behavior like this is what you hear people talking about when they're talking about a cusp, but technically this is also a cusp. It's a pointy spot on the graph. And this guy would be associated with a vertical tangent. So if you allow the derivative to take infinite values, then we could maybe patch this one up, but there's no patching up these guys. And this graph is continuous, right? This function is continuous at all three of these points. So it's not like we're failing to be differentiable because we're not continuous. We're failing to be differentiable despite being continuous. Certainly any discontinuity is automatically a place where the derivative is going to be undefined also. So more non-smoothness. We did something like this. Certainly this would break the definition of the derivative. And then if you had a vertical asymptote, that's no good. Even just a hole, automatically you're not differentiable, whether you've filled in that hole elsewhere or not. So also, right, again, this is the original function, y equals f of x. Just another set of examples of places where this function would not be differentiable. Here, this is no good. Certainly here, here, and here. All of these are places where the function is not differentiable. Right. So in the first graph, the function is continuous at all of those points, but it's not differentiable at them. In the second graph, we're discontinuous. We're discontinuous at these points. And if you're discontinuous, automatically you're not differentiable. So these are the sort of non-smooth behaviors that we're worried about. These are the sort of things that can ruin the existence of a derivative. Questions on this?
So differentiable, does that speak about the entire function as a whole, or are we only ever talking about specific points? Because like, for example, with the absolute value, like it wasn't differentiable at 0, but we said that it was differentiable everywhere else. But would we call that a differentiable function?
No. So this is a good question. Differentiability is a local thing, right? You are differentiable or not 1 point at a time. I'm glad you asked this. So your book does define this. We say f is differentiable on the interval I is generally going to be an open interval, but on the interval I, if f primed of x exists for all x, which are elements of that interval I. And then we say f is called differentiable full stop, right? So differentiable on the interval I means that the derivative exists everywhere on that interval. Differentiable without any qualifiers, like at x equals 5 or on the interval 2 to 7. If you just say f is differentiable, this means differentiable if f primed of x exists for all x in the domain of the original function f. So when somebody says this function is differentiable, without any qualifiers like at 3 or on the interval, blah, blah, blah. If they just say f is differentiable, they mean everywhere in the domain. So yeah, this is not a differentiable function because there's lots of points in the domain where it's not differentiable. This is not a differentiable function because there's lots of points in the domain where it's not differentiable. The absolute value function, we would not call that a differentiable function. Even though it is differentiable at a bunch of x values, it's not differentiable everywhere in its domain. There's another word for this, differentiable at every point in its domain. No, I shouldn't say that. I'll just leave it like this. It's called a C1 function. Okay. So spotting non-smooth behavior, good skill to have. You want to be able to do that algebraically or from the graph. Algebraically, the type of things that yield cusps. Pull up Desmos for you. Might wonder, where do cusps come from? Well, let's look at this guy. Here's the cube root, right? Imagine, so we know that he's not differentiable at 0, right? We've got this vertical tangent line right there. If I were to do something that made this piece positive, then that would be a really pointy spot. One way you can do that is by squaring everything. So here's a pointy cusp, right, coming from the 2/3 power. This is the same, of course, as x to the 2/3, right? Just algebra. So powers of x, where the power is between -1 and 1, tend to have problems at 0. Another example would be like x to the 4/7, similar issues. Of course, the absolute value function and any power of it. Oh, wait, I fucked up. Maybe not any power of it. Ooh, yeah, no, you square that, he's going to be okay. Just the absolute value function then. Yeah. To retract the power of its statement. All of these have issues at 0, and their shifted versions would have issues wherever the shift is. So yeah. Okay, what else? We need to talk about higher order derivatives. Before we do that, am I missing any fun theorems? Oh yeah, maybe just a little bit more calculation. So we discussed this theorem, right? If you're differentiable, then you're continuous. The converse to that theorem is absolutely not true. Being continuous does not mean you are differentiable, only goes the one way. And we did show that the absolute value function is not differentiable at 0. Clearly it's continuous. We've talked about vertical tangents. I do like the way they show this, right? So the idea behind a smooth function or a differentiable function at that number is that you can zoom in. And if you zoom way in to a point on the graph where the function is differentiable, it will look like a straight line once you've zoomed in enough. The curvature will become unnoticeable. However, if you have a function that is not differentiable and you zoom in on that point, that cusp, that pointy behavior will never go away. Right, so kind of look up here at this graph in part A in the line above. You might think that if I zoom in on this enough, it's actually smooth there. And if the function is differentiable, then it will be. But if the function is not differentiable, no matter how much you zoom in, it will still look pointy. All right. Higher derivatives, relationships to physics. That's really all that's left in this section. And if we finish a bit early today, that's all right. We talked a little bit about the Leibniz notation for derivatives. Let me just say recall. Given a function f of x and its graph, y equals f of x we can express the derivatives f primed of x, that's the first derivative of f. And we said we can write this as d dx of f of x, which is sometimes written just as df dx, or if you're thinking about the graph, you might write it as dy dx. Now imagine you have the graph of your function. You have the graph of its derivative that you've sketched. What happens if you try to take the derivative of that? Well, then you get something called f double prime. And the corresponding notations, d2 dx squared of f of x, or d2f over dx squared, or finally d2y over dx squared. And if you have the graph of that derivative, you can think of the graph of its derivative, that's the second derivative. If you have the graph of that second derivative, you can imagine taking its derivative, the third derivative. And the patterns over here are going to become pretty obvious. You could write that as d cubed over dx cubed of f of x, or d cubed f over dx cubed, or d cubed y over dx cubed. The notations on the right-hand side, the Leibniz notation, all this stuff is kind of clumsy, right? It's cluttery. There's just a lot to write. The prime notation is generally very nice, right? It's super simple. But then as you start getting more and more and more of these things, it becomes clunky and clumsy. So for the next derivative, we don't write 4 primes. We put a little parentheses 4 up there. And this would represent the fourth derivative, d4 dx to the 4 f, or d to the 4f over dx to the 4, d to the 4y over dx to the 4, and so on.
I have a questions. You wrote D, D2, D3, and D4. Is it the same 1, 2, 3, 4, just a number? Look like X1, X2, X3, X4. Those just meaning how just meaning it just a number. It doesn't meaning any other equations, double or fourth. It's just 1, 2, 3, 4. It doesn't mean about the equation have some degrees in it.
So what we're going to learn on Wednesday is that there is actually a nice connection between like how many derivatives you've taken and the algebra of the resulting functions. Kind of one of the things that we saw last Friday was that if you take a derivative of a nice power function like x cubed or x squared, it looked like, remember the derivative of the quadratic looked like a straight line. The derivative of the straight line was a horizontal line. There is a bit of a connection with the algebra there, but really with this notation, with these numbers, the 3 here or the 4 here, just think of it as telling you how many times you've taken the derivative. That's really all it means. There are other notations for this also. There's a special notation in physics using a dot, but I don't want to give you too much. So these are kind of just the most common notations. And yeah, this number doesn't really tell us anything about the equation, like doesn't this 4 here doesn't tell me anything like what the function, the fourth derivative, will look like. It just tells me how many times I have to go through that process to get this thing. Is that an answer to the question? Am I being reasonable?
I still not. I understand it very well, but I think as I learn it on the last class, maybe I can figure out the reason.
Okay, let me look at a nice, clean, clear example, something that we can do this estimation game with pretty well. David asks, how do we get to the double prime? Yeah, what does this mean? It just means you take this derivative, right, which is now a function that we have. You start with your original, you get its derivative, and you differentiate it again. So for example, don't hate me. Let's keep it simple. So let's take the first 2 derivatives of the cubing function. I know that f primed is the limit as h goes to 0, f of x plus h minus f of x all over h. That's the limit as h goes to 0 of x plus h cubed minus x cubed all over h, which is the limit as h goes to 0, x plus h cubed. I'm going to FOIL this all out. That's x cubed plus 3x squared h plus 3xh squared plus h cubed. I just happen to have that memorized, so I don't have to FOIL it all the way out every time. Minus x cubed all over h. And you see that the first and last terms here eat each other up. So we're left with lim h to 0, 3x squared h plus 3xh squared plus h cubed all over h. And now every term here has a factor of h, which I can bring out and cancel with the h downstairs. So when I factor the h out from the numerator, I have left 3x squared plus 3xh plus h squared. That factored h will cancel with the h downstairs. And this is lim h to 0. All that survives is 3x squared plus 3xh plus h squared. And now I can plug in h equals 0. I just get 3x squared. This and this both go to 0. So if f of x is x cubed, then f primed of x is 3x squared. And you might be starting to see some patterns with the numbers that are showing up. Those patterns you're seeing are probably correct. But this is our first derivative. Now, how do I get the second derivative from that? Well, f double primed, the second derivative, this is the derivative of f primed. So I'm going to form this difference quotient limit using this function. I'll write it out. This is lim h to 0, f primed of x plus h. minus f primed of x.
I feel like it's going to follow power again.
Yeah, it is. That's exactly correct. So let's plug in. This is lim h to 0. F primed of x plus h is 3 times x plus h squared minus f primed minus 3x squared all over h. We can factor out a 3. That 3 can come all the way out past the limit. And then x plus h squared, that's x squared plus 2xh plus h squared minus x squared. We factored out the 3. The x squareds go. And that's the pattern, right? Every time you FOIL out that x plus h to the n, that very first term, which is the x to the n, cancels with the thing that you subtract. So here, I would just be left with, I gotta put that 3 out front, 3 times the limit as h goes to 0. 2xh plus h squared over h, which is 3 times the limit, h goes to 0. Factor the h. Cancel with the h downstairs. Send h to 0. You get 3 times 2x, or 6x. So f double primed of x here is 6x. And those are your first two derivatives. And we can repeat this process as many times as we want, right? I could take this thing and run it through that derivative machine, right? That difference quotient limit. And that would give me the third derivative, f triple primed. Anybody want to guess what f triple primed is?
Is it going to be
So remember, this is a linear function now.
12? Oh. But if it drops the power, the x just disappears.
Right. So it would be a constant function, and it's going to be 6. You can also think about it as the slope, right? This is a line, it has one slope. So the tangent line always has slope 6. So the kind of sequence of original function to third derivative here would be x cubed, 3x squared, 6x, then 6. That's not hugely important. You guys are going to learn all about that stuff on Wednesday. Those patterns are nice. I want to make sure I'm addressing David's question. How did we get to double prime? So you get to the double prime by priming, or taking the derivative of the first prime. And this process is repeatable as many times as the function allows, right? Some functions you can differentiate once and never again, right? Maybe that first function isn't differentiable. You want to see something fucked up? This thing haunts the dreams of young mathematicians. This is a function that's continuous everywhere and differentiable nowhere. I could find for you a function who has this thing as its derivative. A function that is differentiable everywhere and whose derivative is the function you're looking at now. This thing is differentiable nowhere. So this process is repeatable, but only as much as the function will allow. Polynomials, rational functions, trig functions, exponential functions, all the nice functions from your algebra classes, this process is infinitely repeatable. I could keep doing this. The next time I would get 6. The next time after that, I would get 0, and I'd just stay 0 every time after that. So functions can be differentiated more than once, as long as they are differentiable. And it turns out the number of times you can differentiate a function is a very important classification scheme in analysis. When I said earlier that a function who you can differentiate once and has a continuous derivative is called a C1 function, there are classes of C2 functions. Those are functions you can differentiate twice, but not 3 times. or C3 functions, functions you can differentiate 3 times, but not 4 times. There are C infinity functions, which you can differentiate infinitely many times. And those are the sines, cosines, e to the x, polynomials, stuff that I just mentioned, where you can do this as many times as you want. Such a function is called analytic or holomorphic. This function, the Weierstrass function, it just exists as a foil. Its only purpose in life is to fuck with people. And I'm dead serious. That's it. That's the only reason. It was conceived of and then constructed specifically as a counterexample. Because people, so Weierstrass, one of my heroes, he came late, right? So early in the game, you've got people like Newton and Leibniz who came up with this idea of differentiability, came up with these definitions and formulas and notation. And then came people like Cauchy and Gauss, who were very, very smart. And they took what Newton and Leibniz started with and ran with it and started like finding all sorts of other ways to describe calculus. And then came people like Weierstrass and Riemann. And those people, they looked at the work of the previous generation, folks like Cauchy and Gauss, and they said, well, yeah, this is good, but how do you guys know any of this is like legal? How do you know you're allowed to just keep differentiating? You keep referring to this function's 5th derivative. How do you know it has a 5th derivative? And so Weierstrass, Cauchy, a lot of people of that generation set about coming up with these nasty counterexamples, trying to create, construct, or understand the possibility, the existence of functions that don't do what you think they should do. There's actually a great book. I have a physical copy here somewhere. If you want to get really good at thinking about this stuff, Dover books, dirt cheap, wonderful, wonderful books. This is one of my favorites, Counterexamples and Analysis. You see it's $10, brand new. It's just full of stuff that isn't what you would think it is. And then analysis is just fancy calculus. Okay, that's enough rambling. Counterexamples are fun to come up with, and sometimes they can be more illuminating. You can learn more from a good counterexample than you can from many examples. But we were told, find the first 2 derivatives of this. Boom, boom. I'd like to talk about interpreting those derivatives as rates of change. Because the higher order derivatives have meaning also. Recall that f primed of x is the instantaneous AINIOUS rate of change for f of x, right? Like the first derivative tells you the slope of the tangent line. That is exactly how quickly is your function increasing or decreasing at x. It's the instantaneous rate of change rather than an average rate of change. That means f double primed is the instantaneous rate of change for the function that it is the derivative of, which is f prime. And so on. F triple primed is the blah, 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 blah for f double primed. Many, many places in the real world, calculus describes physical things, right? Motion in particular, motion of like coffee cups and people and cars and spaceships and stuff. Described very well by Newtonian calculus. The particular example that we introduce rates of change with, this notion of speed and velocity, can be extended nicely. So first, let's look at the graphs. Of the 3 functions we were just playing with. f of x, which was x cubed, f primed of x, which was 3x squared, and f double primed of x, which was 6x.
Sorry, could you put the paper down slightly? I wasn't quite finished writing down the above note.
Sure.
Perfect.
All right. So x cubed has a shape like this. Three x squared has a shape like this. And 6x has a shape like this. It says f prime, f double prime. We're going to talk about this more later, but if you take a point on the graph of f, call this A, you know that the slope of that tangent line is the y value here. Right? This is how we were estimating so if I say this is like whatever it is, I don't know, 3, then this y value here would be 3. And the slope of this tangent line, the tangent to f prime, it looks like it's like negative, maybe -6, something like that, I don't know. Would be the y value here. And you can start, instead of thinking of those one point at a time, you can start trying to think of the whole function at once. So let's look at this chunk of the original graph. It's increasing, right? We're going uphill, but we're starting to curve back towards level, right? So what does that mean? That means, well, we're increasing. That means the slope of the tangent line is going to be positive. We're going uphill, which is what it means to say this part of the graph is above the x-axis. Means this thing is increasing. But it's starting to level off. It's called being increasing and concave down. Again, we're going to talk about this a lot more later. But if you look at this piece, it is increasing, but it's starting to level off, which is why this piece is positive, but going towards 0. You see the connection. So the fact that this is increasing corresponds with this being positive, being above the x-axis. The fact that this is leveling off as we get closer to 0 over here corresponds with this thing getting closer and closer to 0. Finally, if you want to connect with the second derivative, if you have a point here on the graph of your first derivative and the y value there is positive, say 3, and you know the original graph is starting to level off, that means that this increasingness must be slowing down. That means that your derivative is going to be positive, but it's going to be less and less positive as you walk to the right. What does that mean? That means your derivative has to be decreasing, which is why your second derivative is negative. So this, let me say it this way. This guy is the rate of change for the guy above. And this is the rate of change for the guy above. And you can think of that as being like a tower, kind of a chain, if you will. Beyond the second derivative, there are actually some things you can say geometrically, but they're not as anywhere near as important as increasing, decreasing, concave up, concave down. And all of that information you get from the first two derivatives. And I'll explain in great detail what those things are when we get to section like 4.2. The most important single application of this stuff, and I'm going to end after this, comes from physics. We know that your velocity is the rate of change of your position. So here I'm going to let S of t be my position function. Right, it says how far I am from home. If I started over here, but at some time t equals a, start over here at time t equals 0, then this distance here is S of a. The derivative of this function, this would be the rate of change of the position function. So how fast is your position changing over time? Everybody knows what that is. Feet per second, miles per hour, that's your speed or velocity. And we saw this last week. But what about how fast your velocity is changing? If I'm going 10 miles an hour, and then the next second I'm going 20 miles an hour, and then the next second I'm going 30 miles an hour, how would you describe that behavior?
That's S of t prime, but to the second. I forgot how to say it.
It would be, yeah, it would be the second derivative, but in common parlance, when you guys have all done this, right? When you get on the highway, you're going from 10 miles an hour to 20 miles an hour, 30 miles an hour, 40 miles an hour. What are you doing?
Increasing speed over a period of time.
Mm-hmm. In a single word, you're accelerating. S double primed, which would be V primed. This is the rate of change for the velocity function. So how fast is my velocity changing? If I'm going 10 miles an hour now, then a second later I'm going 20 miles an hour, second later I'm going 30 miles an hour, second later I'm going 40 miles an hour. I'm gaining 10 miles per hour for every second.
I think it's 10 multiple n.
In the specific example I just gave you, it depends on the units you want to use. You would say it's your acceleration is 10 miles per hour per second. But that's your acceleration. And this is called A of t. So if you're given the position function, you can calculate the velocity and the acceleration by taking derivatives. And learning how to interpret or understand these things as rates of change is central to physics. Really, really important if you want to understand kinematics. So where am I? That's your position. How is that changing? How far did you go over a certain amount of time? That's your velocity. How is your velocity changing? Well, are you speeding up? Are you slowing down? Is your speed constant? Those are all questions about the acceleration. If you're speeding up, your acceleration is positive. If you're slowing down, your acceleration is negative. And if you're staying at a steady speed, your acceleration is 0. You can go further than this. If you ask, how is your acceleration changing? This is kind of silly. There isn't an accepted notation, but this is called jerk. How fast is your acceleration changing? And it gets even sillier from there. I think the fourth derivative, this is called snap. And then some assholes at MIT decided to call the next two crackle and pop, like after the Keebler elves. You're not responsible for these. You are responsible for these. Okay. Yeah. In fact, so here's a fun game, right? If you're accelerating at a very reasonable pace, think when you get on the freeway, right? When you get on the interstate, you go from like 30 miles an hour to like 70 miles an hour, and you do it fairly quickly over a period of a few seconds. So let's say you gain 40 miles per hour every 20 seconds or something like that. That's a little less than 1 G of acceleration, right? Acceleration due to gravity, 1 G. If you were to stay at 1 G for a year, right? You know, when you put your foot down on the gas, you feel your back get pressed into the seat. That's the sensation of acceleration. If you were to stay accelerating at 1 G for a year, you would get to the speed of light, almost exactly. It's kind of cute when mathematics works out like that. So yeah, acceleration is a very powerful thing. Your position is very sensitive to your acceleration. Yeah, it's cool, isn't it? Now, jerk, snap, crackle, pop, these other guys, you're not going to run into a lot of applications for them unless you study dynamical systems, certain kinds of mechanical engineering. But you do need to know, for me, for this class, you need to know that the first derivative of your position is your velocity. Even though it's a physics thing, it's so important. I'm gonna talk about it in this class. And you also need to know that the second derivative of position, which is the first derivative of your velocity, is called your acceleration. And you need to know how to understand those in the physical sense. If your acceleration is 0, that means your speed is constant. If your acceleration is positive, that means your speed is increasing. If your acceleration is negative, that means you're slowing down. If your velocity is 0, that means you're holding still. If your velocity is positive, that means you're moving in the positive direction. And if your velocity is negative, that means you're moving in the negative direction. And it would be worthwhile to see how to connect both of those to the position. All right, I'm going to leave you guys here for today. That's the wrap up from section 2.8. Bigger motorcycles are fun, just please be careful. Let me remind myself where we left you guys for the homework. So you guys had some stuff to work on over the weekend, right? That came due today. On Wednesday, we're going to learn our first few kind of shortcut rules for calculating derivatives. If you haven't finished homework 3, the one that came due today, please go ahead and put it in a submission or submit an extension request. I will grant that for you later today. I'll also be publishing homework 4 today, which is going to be covering sections 2.8, anything from 2.8 that we didn't talk about in here, which is not much. And then also 3.1 and 3.2, which are the 2 sections that we'll be learning in the remainder of the week. So on Wednesday, Radha and Natasha are going to show us section 3.1, which is shortcuts for taking derivatives of really nice functions like polynomials and exponentials. And then on Friday of this week, we will be up for 3.2, and that is being done by Nikita. So I do need Radha and Natasha, please send me all of your materials so I can review them. I would really like it if we could do a dry run, like a test run of that lecture before you have to do it on the spot. That would be best, but at the very least, I need your materials. And then the same thing for Nikita. If you could please send me your materials as quickly as you can, and then come either today or Wednesday in office hours so we can do a kind of dry run and just kind of get all the jitters out, okay? Any questions for me before I let you guys go?
Did you get the email that I sent you?
I have not yet, but I will be getting to my email here in the next few minutes. Is it something you want to talk about now, or do you want me to?
It's the section that I was hoping on doing and project.
Okay, cool. Yeah, I'll as soon as I get to your email in here, I will reply to that. I appreciate you sending it to me. Thank you.
Yep.
All right, anything else I can do or answer for you guys before we scoot? Wonderful, I appreciate that. Thank you, Nikita. Alrighty then, I'm going to go ahead and end the meeting here for today. If you do need to talk to me more about anything else, you can come by the office hour. That link is in Canvas. I'll be there from 1 to 2. You can post on the Discord. You can send me a Canvas message or an email. Otherwise, I will see you guys on Wednesday when we learn from Radha and Natasha how to take derivatives of polynomials and exponential functions. All right, that's it. Take care, guys.
Thank you.